And honestly, so actually, I have, once we get into the actual data and kind of take it step by step, and I have some questions for the audience to think about this little different aspects of the challenges and the opportunities. I don't know, feel free to type right in. Because I think there's maybe a bunch of time afterwards for discussion. And honestly, you might as well just, if there's something that you want to bring up, ask about, etc., you might as well just do it while we're doing this, rather than try to split it apart. So it's fresh in your mind. So the humble plan of the project, and definitely in direct response to needs in the community, is to build a numerical benchmark of cabbing from perhaps the world's longest and most detailed observational record of a rapid tidewater glacier retreat. So basically, to recreate as best as we can from all the data available the dynamic retreat of the Columbia Glacier in Alaska. This tidewater glacier flows into Prince William Sound, and I personally hope that once we'll kind of the idea is that we'll release early and then iterate later. I don't think I see it as a data set that's fixed, but I'll do my best to organize all the necessary people together and all the data together into a data set that can certainly get us started, and it'll probably be plenty overwhelming for every model that exists now, and then would evolve with time, and hopefully we won't have to duplicate effort around this particular glacier. So I'm sort of imagining some bit of community organization around making it this a really truly a benchmark for our efforts. So we've talked about maybe doing this within a year. Don't hold us to that, but that's kind of the timeline we're hoping for. So Columbia Glacier's vast data set is a result of work by many, many people over many, many years. This is not nearly a complete list. So unfortunately, they both passed away recently, but Mark Meyer and Austin Post can be credited for really at the USGS in Alaska premeditating the onset of the retreat and establishing the scientific program way at the beginning, and catching a little bit of what you might sort of consider the steady state. And it's been ongoing ever since, at different levels of intensity through the years. Bob Krimmel, who cataloged the glacier's retreat for many, many years. And so I've put in orange the folks on this list that are present. So that's me there. Tad unfortunately couldn't make it, but I'm giving him a cameo appearance. Shad O'Neill, where's Shad? Okay, so between the two of us, I'd say we're probably most familiar with the data as a whole. So if there's ever any questions, either of us. And then Kevin Walter has also been involved with seismic work back around 2009, 2010. And Gaël Durand, who I've been working with now. We're starting getting going together. He, as a modeler, in comparison to a lot of people on this list, to work with me to, at least for the first part, to make sure that these products that I'm producing are physically consistent, and then the hope is also with input from all the rest of you during this weekend to make structure the data set that best suits the needs of modelers, so you can hit the ground running once it comes out. Okay, so let's go way back as far as we can at the Columbia. So this is the last glacial advance during the Little Ice Age. From here you see some of the dates. This is all reconstructed by Greg Wells and the group at the Worcester Tree Ring Lab from trees that were killed by the glacial advance and then have been since previously uncovered. This is the record of advance that actually Faiza, in her paper in 2007, with others, try to reconstruct this history. So this is the advance premeditating the retreat. And what's interesting to note is that the advance was about on the order of 36 meters per year during the Little Ice Age, reaching in about 1808. That's certainly the day, at least the day we have there, at the position that we found it. I guess Westerners found it when they arrived in Prince William Sound, and right up to modern times. Starting about summer 1982, I'll go some more detail about when we start looking at the actual data. Retreat, the glacier switched from a fairly well-behaved coastal marine terrain glacier that was about a city state to a rapidly retreating one. And it's since 1982 retreated at about 600 meters a year and thinned at about 15 meters a year at the current terminus. So to put things in perspective, it took about 15 years to reverse those 700 years of global advance that I showed you. It's 2001, and this 2011 Landsat photo, more or less, it's actually retreated more since, but that's about where it is. So 1,000 square kilometer glacier has, at different times in its history, contributed about 1 to 2% of new water for the entire world. And I think if we're serious about predicting future rates of sea level rise, as we all know, we have to have some sense of be able to predict whether and when and how quickly other glaciers will do the same. Okay, so some of the data. These 4 panels that we have, this is velocity in red at it's along the center line, but average for the first 5 kilometers relative to the terminus, which is changing through time, then the next 5 kilometers and the next 5 kilometers. And this is to highlight the acceleration of the front and then the overall velocities. The terminus retreat, so this is advance or retreat just sort of geometrically of the glacier changing with respect to the terminus positions. And then water depth, and then I've also put in the flotation ratio sample along the glacier front. And then this is through time from 1980 to present. So we have a few years of basically you have some sort of seeming stability. You have overlaid on this, you still do have seasonal variability of the front and of velocities. I mean, at the Columbia, it's always been pretty much a spring speed up and then a late summer terminal advance. So you have retreats. So you have advance and then and speed up, and then you have retreat of the front and a slow down. And in right here, summer 1982, and it's even more convincing if I zoom in, but you have suddenly a change of behavior that pretty much continues on until recently when the glacier came again onto sort of found at least temporarily stability once again. So basically, there's in the onset of retreat, we observe. We have the seasonal fluctuation starts to grow wildly in relation to the, okay, so the glacier was, for a long time, the terminus position was stable from about 1800 to 1980. And it was on a terminal moraine. You're driving seasonal fluctuation in the front position, and at the same time, you have a fairly gradual thinning of the lower glacier. So from about we don't have very much data in the early years, but from 1957 to about 1980, you have a thinning overall of about 20 meters total. And when overlaid with a seasonal fluctuation in the front, ultimately the front drops back enough that it doesn't recover after this late summer retreat to return back to the terminal moraine, but actually drops off into an over-deepening. And we see observe here the flotation ratio at the terminus to really suddenly drop right in summer 1982 to actually dip below this sort of potentially magic number, but this is 4/3 of flotation ratio, which I mark here. It certainly seems to have relevance for Columbia Glacier, and it's in reference to TAD's criterion for the irreversible tidewater retreat. So this is in relation to if you have a sliding law that's related to effective pressure. So anyway, so starting from this moment, it starts to look like a harmonic oscillator. So we have the same seasonal, the timing of the variability is about similar through the record, but the fluctuations start to grow in relation to the stability of the terminus itself. So we have this episode here. You can see that we have gaps in data in terms of the height of the terminus, all things that we can work to fill. And there's another moment here where I'll be talking a bit more in detail about this episode, more modern episode, where it actually dips dramatically, falls back dramatically into an overdeepening, and is very much a wide-scale flotation of the terminus region. And then just recently now, it back up at around 4/3, again a flotation, reaches a sort of a seeming stability. You have dramatic slowdown, reduction of the variability, and in a way, sort of quasi what it started as before summer 1982. The glacier otherwise is still thinning, so it might be reaching below again a threshold. There's going to be another over-deepening. Now is nearly as deep, but of course the glacier since is also thinned a whole lot, and so relative to its own geometry, there could still well be some more potential for rapid retreat all the way to the actual shoreline of the bedrock, another 12 kilometers from its current position. So you saw the dramatic seasonal variability. I think that's really important to keep in mind with a data set like this. So depending on where you're going to sample, you have a huge risk of aliasing if you're undersampling that seasonal variability. As an example, this is that period from 2003 to 2010 when the glacier went from nearly floating, so at 2005, and then comes afloat and then is ground again in summer 2010. And we have these annual, either paired measurements of retreat and velocity, and so these are basically stereo photo flights. And for velocities, we require a really short time window because the glacier is moving so quickly that the features that you were looking for either they're going to be deformed or they're going to run off the edge of the glacier. That makes it a little bit trickier when you then have to. So we have if we are sampling things on short time scales, this is looking at retreat because actually we have the luxury with retreat to compare between whatever arbitrary times, right? I mean, we're still going to measure the terminus position. We don't have to have the same parts of the glacier to compare. So we can see how looking at annual cycle, you get this fairly easily interpretable signal of this is a retreat sort of reverse, I guess, the retreat speed up. And then if you just look at the very short time slices, you could get all kinds of might even seem like arbitrary values. There's such an enormous fluctuations that are in magnitude larger than the maximum rates of many other glaciers within a given year. So just to give you a sense, this is if I looked at the Landsat repeat images and measured a terminus retreat rate from those. They just happen to be in March of any given year, and you get a totally different answer, right? So this is saying that the glacier is advancing 6 cubic kilometers per year, during that period. So we have to keep in mind that we have an enormous amount of data of the Columbia Glacier. Some years the variability is well resolved. Other times when there's a lot of undersampling, we have to be really mindful of what time of year we're sampling and what the possible errors are of that. So I'm going to pass around this little guide. I'm going to basically pass around a copy of this slide, and you can follow along as we go through some of the components of the data set. So I won't return this slide, but maybe you can just check back and just feel like you kind of know where we are and what's available when. Whoops. So thanks to the foresight of our predecessors, so again, the data begin, the regular observations begin in 1976, a few years before the onset of the retreat, per se, all the way to the present day. Mainly, the geometry and the velocity of the ice are recorded in a time series of vertical stereo and mono, as in, sort of, what I mean by that is just, you don't have stereo views, so you wouldn't be able to get a DEM, a map of elevations. And the combination of those. What's pretty remarkable is during the USGS program, which ended in 2001, it's really during this period that we have the most data, the most sampling. And it's really been since the end of the program that we've been struggling to get to fill gaps. So these are all the velocity intervals that come from a combination of aerial stereo photographs. The red ones are the ones that, I'll come back to that. And then now, since in more modern days, it's the beginning of a worldview record, whenever we can get one. I don't fully understand how one eventually gets access to some satellite imagery. It seems like it's if you're lucky or not. I'll be curious to know from some of you if there's things that I don't even know about that could potentially be useful to add to this list. And then Landsat, as that begins in the 80s, and there's available imagery for that, and Terasar. And so that's also there's no, as far as I know, there's no DEMs that were collected along with the Terasar, but and these have been used to get full glacier velocities. And that's become more and more important in recent years when we don't have this really, really regular acquisition of vertical air photos. I'll be talking about these different components in detail, sort of one at a time. Here we go. Well, so this to give you an idea. So we have, this is from like, I think it's a total of, I have it written down, 265 velocity fields, and 133 of those are more or less full glacier, but all the others are just really focused at the front. And then for elevations, about 148 maps of elevation, but unfortunately, only 2 of those are the full glacier, and actually there's one from 1957 and one from 2007 from Spot. And this is showing their difference. This is to show just what's currently, I believe, is still currently installed, but Shaq, correct me if I'm wrong, at the Columbia Glacier. So we have still a time-lapse camera here, and now one looking back. Is this still going? Juncture? What's that?
Wrong place.
It's been moved.
Next tributary,
yeah. Yeah, okay. And then the web camera still?
Yeah.
Okay. And this is showing the approximate shoreline. And a weather station whose dates I was hoping to share with you, but the website is currently down to know exactly when the different instruments were active. The difference of these two DMs is on the order of 160 cubic kilometers of ice. The difference between 160 cubic.
You mentioned seismometer.
Yes.
Where are they installed?
Now it's just so there's one where so first the 2004 2005 is a network of them all around the terminus.
On the ice.
No, on bedrock.
Okay.
Yeah, and then in the second interval, it's a single one at base right there, or no, here. There we go. Yeah. So with the data set, I think the primary task is obviously representing the evolving geometry and velocity of the Columbia Glacier through its very varied history. Long before your sheet begins, actually photographers are already paying visits to the Columbia Glacier. This is at least the first one known to me by Azahel Curtis in 1887. And then after him, there'd be a number of other photographers, G.K. Gilbert, William Osgood Field, Bradford Washburn, NOAA, USGS, UW would be sending planes There's little bits and pieces. A lot of the work, bringing a lot of those together, was done by Austin Post, and then this is one of the maps I have from him from 1975, a published map, that he used a lot of the early imagery to recreate positions of the front in those years before we have the regular observations. Honestly, a lot of the photos that he uses in this, I've not been able to even find. I'm sure they have to be somewhere. This is an idea of just the terminus position we saw at the beginning, and adding on whatever we can. So this is from 1910, those really early positions, and you can actually see in the really early terminus positions still this behavior of forming embayments during the summer and the recovery of from those embayments, what eventually does not happen in 1982. I like this one a lot. Again, this is, these are the different maps that I've digitized and so overlaid over USGS topo here. This one, unfortunately, is the only one that's really actually very poorly ground controlled. So it's hard to really know exactly the quality of the measurement, but it happens to have, as in my knowledge, the first velocity vector of the Columbia, where it comes out to be about 1.7 meters a day for a feature on the moraine from 63 to 64. What this, of course, means is that with a lot of these images that Austin Post and others were using then, there's certainly possibility, with great effort, but the possibility to get velocities at this sort of pre-retreat state. I'll be throwing out a lot of this kind of thing, like it's possible with effort. What are the priorities? So start thinking about that perhaps. So the vertical imagery. So the potential vertical imagery is obviously the glacier outline, velocities if you have repeats that are close enough together in time, elevations if you have stereo. We have a lot of data of the lower glacier. Of course, that moves with the glacier through time, and so that's really the domain ends up being the entire glacier because the front has retreated so far. We only have another place where I'd love to know if there's something that exists that I don't know about is there's only 2 full glacier DMs of the Columbia sort of known in the community, which seems a shame. And I wonder if maybe Aster, the original imagery from some of these big DM programs, might shed some additional DM opportunities. And then really now, especially in now we had, there's 3 years of TerraStar X, mainly and the velocities from those, from Ian Jochen. And then Birmingham has done a lot of work with getting a lot of the Lanza images into the record and getting velocities from those. Of course, we don't get corresponding DMs. And I should note, remember, like the thinning at any given, at the glacier terminus can be on the upwards of 20, 30 meters in any given year. So it's a rapidly evolving geometry. This is what the modern TerraStar X velocities look like. I don't know how long or if it's really going to be getting more of those, but at least we have, for the first time, some really solid full glacier velocities. The Landsat velocities are not quite as watertight. But to give you a sense of the change in the domain, actually, let me preface this. No. If you look at your sheets, that first section where it was all the USGS flying all of these photo flights, all the ones in red have never been scanned, and so you can imagine that pretty much is not, the data that exists is not in the digital format that we've all come to enjoy, and it's regular, gridded. This is Robert Krimmel, USGS, using analog stereo plotters, hand picking elevations and velocities wherever he thought was important from these flights. And so I've started working on trying to actually digitize the entire record into things that we would recognize today, like DEMs and regular velocity grids. So that's why I wanted to point this out. This is his work, and it's incredible. And it does mean, though, that there's, we can certainly get more data out of that imagery nowadays with automated methods. You can get a sense of how varied his picking of points was and also how the domain changes through time. And then now this is the TerraSARX data from modern time. So, when you have 120 flights to process into DMs and velocity fields and orthophotos, I've been looking for a way to automate this, and actually just pretty much a week before I left for France, came up with something that seemed to work pretty well and pretty much needed very little input from me. So I wrote some code to detect fiducial marks. These are things that in the film days are basically in the camera, and the camera takes a picture of itself, so it knows exactly how the film was laid into the camera. And then we're scanning them, so of course then there's some wobble from that. So finding them and then normalizing the photographs means that you get, it's like you had a digital camera. So the sensor is very, very fixed geometry, and it never changes between the images. That's what we're after. That's all easy to automate. Then that's run through a structure for motion algorithm. Nowadays I'm using Agisoft PhotoScan, which makes it nice and easy. And you're solving for camera and scene geometry that is self-consistent. So you're solving for the position of the cameras, you're recreating the scene that gave rise to the images, and you're all doing this in a model coordinate space. Finally, then you export, you produce a 3D mesh of the terrain, and in this case, I'm running a mesh alignment routine. I'm actually using a non-rigid method, so I'm fitting the glacier DM, which includes some bedrock each time, thankfully, fitting that to a reference bedrock DM, whatever we choose that to be, so that they are as well aligned as possible. And pretty much the only thing that I have to do is pick 4 points between the 2 DMs, and then I have to get close enough, and then it just kind of iterates and finds the best fit. So I'm actually, for the first time, I feel confident that I could actually do this in my own lifetime and get this all done. So some different views of those. And you can see that some of them are really only of the terminus. Others are more extensive. And this is what I'm really talking about. So you're looking at differences between the 2 meshes kind of in 3D. So tangential differences, I guess. The errors, so this is that I'm doing this at 25 times downside from the original images, just as I'm experimenting with the methods. And that result compared to something that's a 20-meter DM is, I think, like 10-meter RMSE, I think, in 3 dimensions. So not just like vertical error would actually be much less than that, especially over the glacier. So anyway, so once process full res, and we actually have full res of the bedrock here, which we don't actually have because all of our modern DMs are up here. That's part of the problem. I think it'll work quite well. So, mainly for my questions for this section are, okay, what other imagery exists, especially when it comes to full glacier DMs? How important is it for processing the early surface into sort of modern format, full resolution products? And I think a challenge that we're going to have to face is how to best use elevation and velocity data that's taken at different times. Between we know velocity at one time, elevation at another, and they're also limited in spatial coverage. So we have very little full glacier data. If we need to create a full glacier domain, how do we combine the two? Or do we leave that up to the models to figure out on their own? So time-lapse is certainly one of the ways that we can help fill out the gaps in the vertical record, but also to get at a higher resolution processes. So the potential of time-lapse photography of any ground-based photograph, really, you can get, even if it's not stereo, you can get terminus position and the height of the ice cliff, just from the fact that the level, the surface of the water. That's a known geometry. You can start to study individual calving events. You can detect flotation of the front. You can describe presence of melange. There's a lot of things that you can see in a photograph just because we're so well suited to interpret them. And you can see that in your timelines, that the record starts way back in 1978. This is sped up a lot. So it turns out we just recently had digitized. We found these old production reels of the best photo per day for nearly 7 years, spanning the actual onset of retreat. The full stands are not that blown out. There's the originals are supposedly every hour for 7 years, but those, as far as I can tell, have been lost. And I mean, these we just finally got digitized. So, I mean, nothing's ever been done with these. There's certainly a lot to be learned from these if we wanted to. Then again, there's another sequence. I've shot every 10 minutes for, I think, about 16 months in total of the terminus and actually other parts of the fjord. They were studying iceberg transport. And these, I mean, this is, so the original's actually been found at Valdez Museum. We're trying to get them scanned. But in this case, these are literally VHSs that were from a Laserdisc, which were from the 35 millimeter originals. It's a lot of data wrangling, and I think just working through a lot of this historic data makes me appreciate the importance of archiving this properly, because it's so easy to lose a lot of what we've already learned. Finally, up to the digital age, then the coverage gets quite good, and starting in 2007, it's actually been so far, thankfully, continuous. Here's an example of that, maybe. And overlaid are some velocity vectors. I've not formalized that, but I'm always tinkering on eventually getting some sort of consistent velocity product for the whole time-lapse record. Can't really see them very well, but this is in 2009 when the glacier is totally floating, and so you get big, large tabular icebergs. And so for this, I've put quite a bit more work on than the historic images. This is all the different views that we have, tracking the progression of the terminus, collecting ground control either in the field or through ortho photos, through Google Earth, flying around and finding summits, and ultimately getting all the images reduced to essentially functions that can start to tell us things about what we might want to know. I'm cheating a little bit. This is actually from Svalbard, but I didn't have a figure on hand for the Columbia. But this is to show that you can get the terminus position, and if you also trace the top of the ice cliff as best as you can, it can be very hard to interpret what exactly that means in some geometries. Then you can get the terminus position, and you can also get the height of the front. And it's pretty much just all geometry, and it's a lot of tracing lines. There's a lot of data. Columbia is one place, but we have time lapses in it's become a very popular form of data. This is an example I'd like to show to give you one example of how we can approach the problem. Until we have automated methods, I guess it's always grad students, but I sort of passed on the work to others working with this platform called Mechanical Turk, which is one of these. There's others like it, online marketplaces, or sort of a workplace where you can hire out human effort. It's used a lot by the computer vision and linguistic communities to farm out essentially small tasks that computers can't still perform, but humans are very well suited to performing. Glacier terminus tracing is certainly one of those. And as we run this out, so this is 1,680 daily terminus positions of the Columbia. You see those early data gaps. As the terminus gets further away, if there's a presence of millage, and it's really hard to know what you're actually looking at to define where the terminus position may lie. You get obscuration from if you have too oblique of a view. Mainly your sources of errors are if you have too much of an oblique angle, distances to the terminus, whatever you're trying to measure, and difficulty in interpretation of where we might actually place the terminus position. So you can see different people are struggling to identify what is a terminus and what isn't. And I would have trouble as well. Okay, this goes on for a little bit, so we can move on. Anyway, it looks like that. And just to just give an idea of certainly one way we can start to get at, processes on different time scales, recreating, either from the occasional vertical data as well as time lapse, we can give us down to. I think that we have some that we're running at every 45 seconds in different periods, and then using them to both. So this is just checking results between the different data records. So that's satellite and aerial derived terminus positions, but also interpreting what we might be other data we might have in the context of an image can be also quite enlightening sometimes. And finally, I will mention, I've been trying to woo different computer vision scientists to work on some of these problems, thinking that we have a lot of imagery that's a lot more interesting than a lot of things they work on, like architecture and toy models of dinosaurs. Although dinosaurs are pretty cool. And what this essentially we have, what it is essentially is a benchmark for their methods. So a human verified of, say, of terminus positions, for example, they can develop algorithms against that and train them against work that we have already done. And I sort of see that as certainly part of the data set, obviously in a very different direction, but all part of the collective effort. So the question really, and this is hard-earned data, I would say, with time-lapse. You can tell just from the lack of information that's come out of the time-lapses in terms of quantifiable data points. Over the years so far, I think we're making some progress. So, which particular things on what time scales, like every 45 seconds, every minute, there's certainly a choice when it comes to this imagery is the most relevant to evaluating models. And I'll throw out, what role could crowdsourcing, computer vision, algorithms play in processing time-lapse glaciers and to grow that kind of data availability. We have a lot of pictures. I mean, a lot of people are using these methods. And there's a lot of work to be done, I think, a lot of untapped potential. So the bed obviously is crucial. And a brief history. There's been a lot of early surveying. It's been very difficult to interpret the results of some of those. I think the errors are very large. And really the first is in 2005 when NOAA ship Rainier went in doing a sonar survey of the whole forebay up to the terminus at that time. So leaving out, of course, a lot of the glacier bed, which is under ice. So in 2010, Conway and others went and flew this here plane. Did a few flight lines on the lower glacier with radar. And these are different inputs that went into Bob McNabb's full glacier bed using continuity of mass assumptions and data constrained by the data I mentioned. And this is the state of the art when it comes to Columbia Glacier bed. I think this is one place that there's going to be some evolution. Will be improved. Comparing the spot DM to this, I found that there's some very obvious artifacts that just basically got embossed right into the bed. So there's little things like that, and then more disruptive things. So this figure got a little bit corrupted, but well. So first, from the WISE program, they were reporting differences up to 500 meters. That's all relative to the modeled bed. That's all in the very upper branches. Maybe more significant for actually modeling the past retreat of Columbia Glacier is work by Katie Bolt and others. She just sent me this right before I took off for France. They'll be publishing this soon. They found from seismic surveys 3.2 times 10 to the 8 cubic meters of fine-grained sediment in the forebay. So up to 50 to 100 meters thick in places. She sent me. So this is the 2011 surface from their survey, and then this is the bedrock line. This is depth time from from one center line right in the forebay region. Which means, of course, that the post-retreat bathymetry, like what NOAA mapped in 2005, for instance, is not representative of what came after or what came before. So the glacier might have been seeing a very different, they've been occupying a very different bed than we see now. So then, how valid is our assumption of a static bed? Perhaps not, at least maybe not significant in terms of the bed motion, but in terms of knowing what the glacier was resting on at the time. And then one concern I have is how do we keep the data archive updated with the latest measurements and methods as that evolves. Finally, we do have some periods in the Columbia Glacier record where we can say something about the statistics of individual calving events. So there's the seismic data for sure. We also have these two. In June 2005, basically Shad and others were recording individual calving events. And then again, in 2009, there was a camera that was running every 45 seconds. And that's enough to actually resolve individual calving events. There's so many calving events in Columbia that anything much longer than that, like 10 minutes, 20 minutes, it's actually pretty hard to decipher individual events because they're happening so frequently and they're superimposed on each other. These are sampled from very different environments. I couldn't get at the 2005 figure, but so this is a map from DEMs and the modeled bed. This is looking at the flotation ratio of the glacier on different 100 by 100 meter cells, which is what Bombing Dam has its bed on, which pretty much defines the grid for everything else at the moment. And then these are where the ice is actually floating. So in 2005 would have been right a little bit before then, where the glacier is just barely not floating. During this time, there was observed through the seismic work that Fabian and Chad, smaller, more frequent calving events. In 2009, the glacier is still very much floating at the terminus, and you get fewer, larger events. You can do different. It's very, very difficult with photography to measure the volume of an event. A lot of the events are going to include some, but you don't know quite what proportion of underneath the water volume, something you can't observe. It's very, very useful to have direct observation in terms of judging in real time the magnitude of an event, and very difficult from just purely a time lapse to really get a sense of the size of that event if you don't have the acoustic data and all these other things that affect your sort of cognition of the calving event. But for the time when they were doing direct observations, there was a lot of pictures that were taken, and together with the observation description of the calving event, I was able to put together basically a calving event volume distribution. And this is overlaid with a bunch of other data. So Jan Ostrom and a bunch of us observationists are putting together this data on calving modeling and observations. And Columbia, at this time when it's very near flotation, spans the magnitudes of calving event sizes to connect kind of these grounded glaciers in Alaska and Svalbard with Greenland outlet glaciers and yes.
Sorry, what is
N? Frequency. Sorry, this frequency distribution of different sized events.
Okay, so it's just a distribution.
Right, it's a distribution
PDF
of frequency.
Or,
sorry?
It's a PDF, probability density function, or it's a cumulative distribution?
Not cumulative. So this is just showing for any given volume, this is the relative frequency. So I think what's important in terms of for the modeling aspect is that the Columbia Glacier at this time, for instance, anyway, in 2005, was capable of anything from sort of one particle size to actually there's a single calving event that was observed at 10 to the 8 cubic meters, which is basically the entire front of the glacier going all at once. in an ideal world, potentially the models could be made, could be expected to reproduce the full range of behavior of a given glacier condition. This is the inner event times at Columbia Glacier. So these are different records. It's kind of hard to tell. These actually agree very remarkably well given how different they were collected. But in 2005 and 2009, you can see that actually there's a large relative increase in the largest events, and the corresponding decrease in the smallest events. In terms of time between, this is time, so not magnitude. But sort of longer time between events, they also happen to be larger, but I don't have that data shown on here. The seismic has trouble resolving the smallest events, but has a much longer tail because of a much longer record. I'll note one thing is that if you look at the precise timing in relation to the tides of these different events, in 2005, when it was very, very close to flotation, there was a tidal signal. And actually, the calving is more likely to occur, about 25% more likely to occur during high tide than after in 2009 when that sensitivity totally disappears, which makes sense since it was very much afloat. And finally, another kind of data we might have is the size of the fragments themselves of the resulting icebergs. And in the Terrasar X, this is, I should have zoomed in a little bit, but it's demarking different specific icebergs, trying to avoid getting confused by the melange, and it gets a particular, also very power law distribution of the fragments that result from the calving at Columbia. And again, this is the kind of data that, the statistical distributions that we might want to reproduce in modeling. And anyway, I'm happy to provide them. So finally, in terms of the data set, we want to have them be standardized, same coordinate system throughout, expressed relative to the, finally I'm thinking the geoid, to avoid confusions with the water level, available both on the common 100-meter grid that the bed is expressed in, but also because I think in-house, it'd be much harder to compare different results from different modeling. If everyone's doing in-house interpolation, but also I think all the information that goes into producing those high-level products should also be included, along with the full recipes. And right now, what we've been talking about is having two sets, Gala and I, one with basically constructed around geotiffs and shapefiles for modelers, NetCDF and ASCII, and having both sort of the raw and the gridded versions of the data set. Maybe a bigger conversation is really how to administer and host this data. I'd like it to be free, public, online, easily updated because surely there'll be more data and also better understanding of previous data, and some way to collect community input and a way for people using the data to communicate amongst themselves. So I'm sort of providing either the independent route NSIDC. There's a lot of sort of open data portal type platforms coming out kind of in real time right now. There's different choices. And maybe a much longer term question is how to rate and actually archive the model results from the use of this benchmark data set. So there you go. Questions, comments?